we're going to take a quick look at discrete random variables and how to compute the mean of those values. So first, we're going to just kind of look at some vocabulary. A random variable, it's a quantitative variable whose value depends on chance. So this term quantitative right here indicates that we're only working with things that are numeric in nature. We're not going to be working with categorical or qualitative variables. Now, a discrete random variable still has all the traits of a random variable, but the difference is that all possible values can be listed, which is what makes it discrete. With the notation, we're typically going to be using capital letters to represent our discrete random variables, and I'll show you that in just a second. And then we're going to look at how do we make a probability distribution. So what this probability distribution is we take all those values that can be listed and we put them into a chart along with their associated probabilities. So it's usually going to be in the form of a table. Doesn't have to be. It could just be any listing of those values and their corresponding probabilities. Okay, one thing after you get this listing made, you can always check to see if you're on at least the right track by adding up the probabilities, and the total should be 1. Now the reason it should be 1 is because all possible values can be listed, which is what makes it discrete. Then we should have all of our data represented within our probability distribution, so we should have everybody accounted for. Once we get that probability distribution, we can then often use it to make a probability histogram. So here's going to be our first example. A survey was conducted, and we're going to let X represent the number of siblings. So you can see right here, we have our capital letter X to represent our discrete random variable. And the reason this one is a discrete random variable is you can see that our values are all numeric. So when they did this survey, when people answered their question, they would answer with a number. Okay, and it's discrete because we have all of the possible outcomes listed here. So for this survey, our lowest value was 0, our highest value was 4. We were able to list all the possible outcomes there. So what we're going to do now is we're going to take this frequency table and we're going to change it into a probability distribution. Now the tables look quite similar. We're still going to have our list of X values over here. So we have 0 siblings, 1, 2, 3, and 4. And now over here, we're going to have the associated probabilities. Now, when we are doing this, we have to take our frequencies and transfer them into probabilities. Well, in order to take our frequencies and change them, we need to first know how many total people were surveyed. So if I find the sum of the frequencies here, I find that there were 170 people in my survey. So that would be the total of all my frequencies. Now, in order to take these individual frequencies here and change them into their probabilities, we would need to find their relative frequencies. So I would take 32, my frequency here, divided by the total of 170, and then divide those out. I'm going to round my values to 2 decimals, and my relative frequency turns out to be 0.19. So what that tells me is that for this particular survey, if I were to randomly select one person's response, there's about a 0.19 chance that that response would be somebody that answered they have 0 siblings. So this relative frequency is the exact same as my probability value. Okay, and then I'm going to do that for each of these. So I would take my 47 divided by 170. And continue all the way down the list. Okay, and then I can transfer them over here. And here I have my probability distribution. So you can see I have my discrete random variable X, which again represented the number of siblings. I have all those possible values, and I have their associated probabilities listed there. Now, if I take that table with all those probabilities listed, and I now change it into a histogram, I will have that probability histogram. So you can see across the bottom, I have my values for my number of siblings. Across my vertical axis, I have the associated probabilities, and then these values correspond to the heights of the bar. So this is what your probability histogram could look like, and this is a version of a probability distribution. Okay, so now we're going to look at an example where we're going to look at flipping 3 coins. Now you'll notice here we have our discrete random variable with our capital letter. It says let x represent the number of heads in one trial. So I'm going to jot that down up here, that x equals the number of heads. Okay, and what we're going to be doing is we're going to use the sample space. So we're actually going to list out the sample space this time, and we're going to use that to create a theoretical probability distribution. So what you want to do is you want to think about what are all the possibilities that could occur if you were to flip 3 different coins. So you could get 3 heads in a row. You could get 1 tail and 2 heads. You could get heads, tail, heads, etc., etc. So you would keep listing these out until you have all the possible outcomes listed. Okay. Once you get them listed, now we can go ahead and come back to our table, and we can use our sample space in order to figure out the values of our table. So as I look through this, I could potentially have 0 heads that show up. I could have 1 head, excuse me, that shows up. I could have 2 heads, or I could have 3 heads. So 0, 1, 2, and 3, those are going to be the x values in my column over here, because remember, my discrete random variable is the number of heads. Okay, so I could possibly have 0, 1, 2, or 3. That does not show up very well, so I am going to make my table right here. Okay, 0, 1, 2, or 3. Now, in order to figure out the associated probability, I can come over here, and I have a total of 8 outcomes. And out of those 8 outcomes, only 1 of them had 0 heads. So my probability of getting 0 heads is 1 out of 8. Okay, now to get 1 head, there's 3 possible ways for that to occur. So the probability of getting 1 head, exactly 1 head to show up, is 3 out of 8. Okay, similar with 2 heads, there's 3 possible ways for that to occur. So I end up with 3 out of 8. And then 3 heads, there's a 1 out of 8 chance. So here we have our probability distribution for flipping 3 coins. Now we're going to take a look at how can we find the mean from a probability distribution. So the mean is often also called the expected value. So if you happen to see the phrase expected value, it is referring to the mean. Now I'm going to do kind of a side example here first, so that way when we get to the formula, we can maybe have a better understanding of where the parts of the formula are coming from. So let's say that we have 8 students listed, and then we have their ages listed. If we were asked to find the mean, we could go ahead and just use our standard formula where we add up all the values. And then divide by the total of number of values that we added together. And that would work out just fine. If you do that computation, you end up getting 13.25 years for the answer. But now, what I want to do is I want to kind of break it down a little bit and look at the components here. So when I have repeated numbers, so I had 3 10s, I can write that a little more simply as 10 times 3. So repeat addition I can write as multiplication. Similar with my 14s. I have 2 of them that are being added together. So I could write that as 14 times 2. And the same thing with my 16s. There was 3 of them, so I could write that as 16 times 3. Now again, that would still all be divided by 8. I'm going to go one step farther, and I'm going to break these fractions back down into just individual fractions. So this first one here, I'm going to put it as 10 times 3, and I'm going to give it its own denominator of 8. Same thing with the second one, 14 times 2, still has its own denominator of 8, plus 16 times 3, give it its own denominator. So I've taken this top fraction and I've just broken it back down into its individual pieces. And now what we have here is kind of an interesting thing, because if we were to make the probability distribution of our values, it turns out that based off of our data set here, the probability of randomly picking somebody that was 10 would be 3 out of 8, because there's 3 10s in our list, 8 total options. And what I want you to notice is that this 3 out of 8 shows up right here, right alongside our 10. So you'll see we have the 3 out of 8 and the 10 right here in our formula. And that same thing is going to happen in our next piece with our 14 and our 2 out of 8. So we have our 14 right here, and we have our 2 out of 8. And the same thing with our last piece. That 3 out of 8 and our 16 both show up right here in our table. Now, if we take a closer look at this and try to maybe turn it into a little bit more of a formula, what we end up having is we have our first x value. So this 10 is our first x value. So I'm just going to call that x1. And then that value is multiplied, by its corresponding probability. So we end up taking x1 times the probability of x1. Then our second piece here, okay, the 14, that's my second x right over here. So I'm going to call that x2, and then we times that by its probability of occurring. So the probability of x2. Same thing happens here. The 16, that's my third x, and then we multiply it by the probability of that occurring. Now, in theory, this would go on and on and on. So if we had a probability distribution that had 10 different entries, we would have 10 different components to our formula here. So what we do instead is we are going to use summation notation to write this formula. So what this turns out to be is that the mean is equal to the sum. So this is the Greek letter sigma. It represents to add all the things up. And notice our pattern. We have x times its associated probability. So we're just going to write that as x times the probability of x. And what is implied with this formula is that you will take each of these pairs and you will multiply them together until you have all of the pairs multiplied. So we do this for our entire table here. So let's go back to that question we had at the beginning where we had the siblings. And if we want to find the mean of the probability distribution that we created, we can go ahead and use this formula and use that to compute our mean. So what we would do first is we would take our first group here, the 0 and the 0.19, and we would take 0 times 0.19. Well, 0 times anything gives me 0. Okay, then I'm going to take my second one here, 1 times 0.28. And that's going to give me 0.28, and I'm going to keep going down my table. So I've gotten the products of each individual pair written down, and now I need to do the sum. So these products, those are this component of the formula, and then the summation is the last part that I need to do. So I need to add all those values together. When I add all those together, I get 1.62. So what I find out is that from that survey that was done here, the mean the mean number of siblings is 1.62 for our particular data set.